Today I'm going to be explaining chapter 3 in chemistry level N. Now, it's mostly all practically just me solving, because the entire chapter is practically just questions that you need to solve. There's no really understanding anything in this chapter. And when it's usually only questions, we'd already have taken the concepts and how to solve them before, and now we just need to focus on remembering how to solve them. So we're gonna start off with the only definition or the only new thing of this chapter. It's the mass spectrometer. It's practically you have to read this paragraph because it practically explains the entire thing. I can't really summarize. Long story short, it's how we found the isotopes and their masses for all our elements. It speeds up the sample, knocks it with electrons, and like I said, read it. That's the only way you'll actually understand it, because I can't really explain it, or I could read it just. Anyways, let's start. A sample of chlorine consists of 1 times 10 to the power of 6 atoms of 35 massed chlorine, and 1 times 10 to the power of 5 atoms of 37 gram mass chlorine. What's the average mass? Now we know average mass is percentage of the first times mass plus percentage of the second times mass. Let's name them 1, 1, 2, 2 over 100. Now that's what we do when we have a percentage. Here we have mass, or like number of atoms, which you could still use. So atoms 1 times mass 1 plus atoms 2 times mass 2 over A1 plus A2. That's how you solve these. So now since we have atoms, we're going to use this formula, of course. So the number of atoms in sample 1 is 1 times 10 to the power of 6, right? Yeah. Times the mass, which is 35, plus 1 times 10 power 5. Oh, usually we use significant figures. You kind of have to, but now since I don't really have the space, I won't. 5 times 37. Then you put all of that over 1 times 10 power 6, significant figures of course, times plus 1 times 10 power 5. And then throw all that in your calculator. You should get an answer of 35.2. Or like when you round it, you get 35.2. Now, you have CQD2, naturally occurring lithium, has 2 isotopes. The average atomic mass is 6.9. So here they gave us the mass of each sample, Li6 and Li7, that's the mass, and they gave us the average mass. So what now we need to find is the percentage. So how do we do this? If you did the IG, a question like this came in the IG. Anyways, so it's percentage, let's name the percentage X, times, I'll just put times as a dot here because we have X, 6, plus, now you're gonna say we can't use X again. Of course we can't. So it's gonna be 100 minus X, because if there's only 2 isotopes, they make up all 100%. So it's 100 minus X times 7 all over 100, because here we're using percentages, equals 6.9. Now, is it 6.9? Yes. Now what do we do next? We do X, or 6X, plus 7 into 100 minus X. 100X, my bad. No, 100 minus X. I wasn't wrong. Then that equals 6.9 times 100, which is 6, 9, 1, 2, 0. Now we need to distribute the 7 into the 100 minus x. So 6x plus 700 minus 7x equals 690. Now negative x equals 690 minus 700, x equals 10. So now we know that the one that we gave x to is 10, and the one we gave, so Li, we gave it x, so this has 10%, and then Li7 is 100 minus 10, which is 90%. And that's how you solve part CQD 2. Now let's go on to CQD 3. They gave us this relative abundancy, and I'm assuming molar mass or relative molar mass. I'm not really sure. No, I'm assuming it's molar mass. I'm assuming it's mass per sample. So here's how much is the percentage abundancy, and this is how much it weighs. Deduce the number of isotopes. Now you're gonna say, oh, how am I supposed to know how many isotopes we have? If we have, this one is 1 line, this is 2 lines, so you have only 2 isotopes. Now identify the elements in this diagram below. It's actually above, but anyways, it's fine. So now we're gonna do the exact same thing we did here, just we use this formula. I don't know why I wrote 6. This formula, now we use it. So first you're gonna have to find out how much is the percentage. Once you draw a straight line from here, you're gonna get a line that reaches here. Let's say 70 is here, so this must be 75. So this line is 75%. And this line here would be like after, no, this is too low. Like after, like if you focus, you're gonna realize this is 25 here %. So you do 35 times 75 plus 37 times 25 all over 100, and this should give you 35.5. Okay, let me just turn off something because it's, no, not turn on, turn off, my bad. Let's keep solving the things that I don't want it to solve. Okay, good. And now, since it's 35.5, they're asking us which is the element. So we have to go back to our periodic table and you look at all the masses and find out which one has a mass of 35.5, which in this case it is chlorine. Now we need to determine the atomic mass of unknown elements in a given compound. Now, for the examples, they're not usually, we shouldn't usually solve them, but it doesn't hurt. I'm gonna probably solve them now. So let's read the full question. I accidentally cut the video off instead of pausing it, but it's fine. So we were on example 1. X of 3 is 50% fluorine by mass. Calculate the atomic mass of X. So we have X and 3F, right? Each one of these has 50%. Now we need to find the mass of X. We know the mass of fluorine is 19. 1 fluorine is 19. So what we're gonna do practically is just cross multiply. So 50 times 3 times 19 divided by 50 should give us 57. So X equals 57 grams. And they don't ask us what compound is this, so it doesn't matter. Now, M2O7 is 76.9% M by mass. We don't know metal M. Calculate the atomic mass of M. Now I'm gonna delete this so we have a space to solve. Now, this is almost the exact same thing. It's just now we have, why is it not zooming? Oh my gosh. Zoomed. So we have M2O7, right? Let me just write it here. M2O 7. So we have 2m. M is like our x, we don't know what it is, plus 7o. And we know that m is 76.9%. So if this is 76.9%, the other one must be 100 minus that. Let me do it on my calculator. 100 minus 76.9, and that's 23.1. 1 by mass. Now we're gonna do the exact same thing, except here we're gonna replace the O with 16, and now we're just gonna cross multiply the exact same way. And we just need to be careful that there's a 2 here. So you're gonna do 76.9 times, this is 16, not 15. Okay, times 7 times 16. Then you're gonna divide by 23.1. And then we divide this number by 2. And we should get that m is equal to around 186.4, but everything we have is still 3 significant figures, so it's just 186 point. Because significant figures. That's example 2. Now let's move on to determining a formula of compounds, which is gonna take up from CQD4 to example 4. Let's start. So a hydrocarbon sample with mass 3 grams underwent combustion, producing 5.5 grams of carbon dioxide. If all the carbon initially present in the compound was converted to carbon dioxide, what was the percent of carbon by mass in the hydrocarbon sample? Now, this question has a specific formula we need to use and we need to memorize. Let me write it here in coral or red, whatever. 2 formulas actually, but one of them is for carbon, the other is for water. This formula states that the mass of carbon equals mass of carbon dioxide times 12 over 44. Memorize it. It's the mass of 1 carbon over the molar mass of one carbon over the molar mass of carbon dioxide. And for water, it's the same thing. Equals, I think it's H2, yeah. Equals mass of H2O times 2 over 18. So we need to memorize these 2 formulas only for this part. Now, the mass of the hydrocarbon had a mass of 3 grams. But we have, okay, so we had 5.5 grams of carbon dioxide. So we do, oh my gosh, 5.5 times 12 over 44, which gives us 1.5 grams of carbon. Now, to find the percentage of carbon, we have to put the mass of carbon over the mass of the hydrocarbon multiplied by 100. The mass of the hydrocarbon was 3 grams. So 1.5 over 3.0 times 100 equals 50%. And that is it for this part of the question. A compound X is 52.18 carbon by mass, 13.04 hydrogen, and 34.78 oxygen. Find the empirical formula. I'm going to solve it down here. Again, for anyone who did IGs, you probably have stumbled across this question like over 1,000,000 times in the past papers. But I'm going to solve it, of course, for people who didn't. So first, what we're going to do is we're going to consider the percentage a gram. We're going to consider each percentage is how much it is in grams out of 100 grams. So what we're going to do is we're going to find the moles, considering that 52.18 is how many grams we have, not percentage. So for carbon, for hydrogen, and for oxygen we have, right? Yeah. So for carbon, we have 52.18. And then you're going to divide it by the molar mass of carbon, which is 12. For hydrogen, we have 13.04. We're going to divide it by 1. And for oxygen, it's 34.78, I think, yeah. 34.78 dividing by 16. This one is gonna give you an answer of, wait, let me do it on my calculator. It's gonna give you 4.35. This is gonna give you 13.04. And this is gonna give us 2.17. Now, what we're gonna do is very simple. Find the smallest number between these three. So 2.17 is our smallest, right? So now we're gonna divide all of them by 2.17. So 4.35 divided by 2.17, which gonna equal to 2. Then we're gonna do 13.04 divided by 2.17, which is gonna give us 6. And we're gonna do 2.17 divided by itself, which is gonna give us 1. So now we know, since this is for carbon, this is for hydrogen, this is for oxygen, this is practically how much it's equal. So carbon we have 2, hydrogen we have 6, O we have 1. So our compound is C2H6O. And that's how you find it. Pretty simple, right? So we're gonna erase everything to make space for the rest of the questions and write down our answer in the question, C2H6O. Now, a sample containing 0.78 grams of potassium reacts with enough oxygen to produce 1.1 grams of a single product A. What's the empirical formula of A? Now, what we're gonna do is, the sample has two things, or it's reacting with two things. It's K, O. But we have the entire sample's mass and we have K's mass. We need to find O's mass. So if the entire sample is 1.1 minus 0.78 is gonna give us the mass of oxygen, 0.32. Now what we're gonna do is the same exact thing we did with the question above it. 0.78 grams over the molar mass of K, which is 39. You're gonna get 0.02. And we're gonna do the same with oxygen, which is 0.32 over 16, which equals to 0.02 also. Now since they're the same, you're gonna divide it by 0.02, you're gonna get that this is 1 and this is 1. So our compound is KO. That is it. Now let's go on to CQD7. A sample containing 0.56 of hydrocarbon X, a compound formed of C and H only, was burned in excess oxygen. 1.76 grams of CO2 and 0.72 grams of H2O were produced. So now, since we have CO2 and H2O, we need to use both of these formulas. We do 1.76 times, it was 12 over 44. And then we do, for the second one, 0.72 times 2 over 18. And we should get, let me do it on my calculator. We should get 0.48 for this one. And 0.08 for this one, if I'm not wrong. So now we divide it by its molar mass to get how many moles we have, because this is grams. So divide by 12 and divide by 1. So this you get 0.04, and this you get 0.08. Now obviously 0.04 is less, so we're going to divide both by 0.04. This equals 1, and this divide 0.04 equals to 2. So carbon we have 1 of, and H we have 2 of. So the compound is CH2, and that is it. Now we have CQD8. They're all the exact same thing, by the way, guys. Like, if you understand one, you don't actually have to solve the rest because they're the exact same concept, but I'm solving them for anyone who gets confused on any single one. A sample containing 0.198 grams of hydrocarbon was burned in excess oxygen. 0.324 grams of H2O were produced. So now what do? We have 0.324 grams of H2O, right? We need to find how much hydrogen do we have. So we do 2 times 2 to them, we multiply it by 2 over 18. We should get, I think it's 0.036, but let me check. 0.324 times 2 over 18 gives us 0.036. And now we have, you're gonna say, okay, we don't have everything. Where are we gonna get carbon from? We said it's a hydrocarbon. If this is the whole thing and this is the hydrogen part, subtract them, you get carbon. So 0.198 minus 0.036 should give us is it 0.08? Let me do it. 0.198 minus 0.036. Yeah, wait. I think it's... I did something wrong. Wait, my bad. In the calculation. Okay, no, nothing wrong. I was just confused because okay, it's fine. So this is 0.162 and this is 0.036. This is for hydrogen and this is for carbon. Now we're gonna do 0.162 over 12 and then the other one over 2 because it's H2. We found H2. When we do this formula, by the way, guys, be careful. When you do this formula for water, it gives you the mass of H2, not H. So, yeah. So 0.036 divided by 2. This is going to give you 0.0135. And this is going to give you 0.018. Obviously, 0.0135 is smaller, so we divide by 0.0135. This equals 1. This equals 0.0135 is equal to 4 over 3. So to get rid of the fraction, we need to multiply this entire thing by 3. So this is carbon and this is hydrogen, right? If you're multiplying the hydrogen by 3 to get a whole number, because we can never, ever, ever have a decimal as a subscript. So we have to make it whole. What makes 4 over 3 whole? 3. Multiplying by 3 makes it whole. So if we multiply the H by 3, we're going to get 4. But if we multiply H by 3, we must multiply C by 3. So we get C3H4, and that is your compound. And that's it for this question. Now, let me first see what the two examples are about, because if they're the exact same concept as what I've been doing since question 4, I'm not gonna do them. Let me read them. Okay, so I'll do example 3, but example 4, I doubt anything like it's gonna come. And either way, it is really easy because they gave us a lot of information about it that would make it way more easier than these where you have to figure out what type of information you even have. So a sample of hydrated CuSO4 with a mass of 25 grams. You're gonna say, okay, so its mass is 25 grams for CuSO4. Wrong. Hydrated CuSO4, so it's chemically combined with water. CuSO4 times or dot, we write X H2O because we don't know how much water yet. This weighs 25 grams. It was heated until all the water was removed. After all the water was removed, it has 16 grams. So CuSO4 normal is 16 grams. Now, what's the formula of the hydrate, aka the water? So 25 minus 16 gives you 9 grams. So the mass of the hydrate, or aka the water, was 9 grams. So what we're going to do is the moles of the water is 9 over 18, which is 0.5. And the moles of the CuSO4, you're supposed to find CuSO4's molar mass, which is 160. So 16 over 160 equals 0.1. We're going to divide each by this. So the water we have 5 and this we have 1. So our compound is, instead of X, it is 5. So our compound is CuSO4 chemically combined with 5H2O. Now let's move on to the rest of these questions. And I don't understand why all of these questions are examples. If most of them are examples, then we don't get how to solve examples in our mark scheme. So I feel like CQDs are more important here. I'm going to skim through each example quickly and see which is actually important or not, because I feel like most of these were things we've already done before a million times. So I'm gonna pause and read the questions and then I'll solve. Okay guys, so after reading like all of them or most of them, I'm not gonna solve them purely because of the fact I don't want to get anything wrong and then like cause everyone else to understand it wrong, because even the teachers didn't solve it in class in our school. So if teachers don't think it should be solved, I don't think, like, if you want to solve it for extra practice, be my guest, but we don't have any mark scheme anywhere. That's why I won't like risk it and like solve anything wrong by mistake maybe. But most of them are very simple concepts we've taken before, so I don't think it will be that hard for anyone who does want to solve them. Now we have CQD 19 and CQD 11. We have to do these. Don't miss them accidentally by moving. And we also have CQD 10 down here. And of course, top questions. But examples, like for now, I'm gonna skip because I don't think any of the classes really have solved much of them. And then we just do top questions and that's it for this chapter, but let's go on to CQD 9. Okay, so we have a gaseous mixture at 25 degrees Celsius and it has 0.5 moles of CH4 and 1 mole of O2 under a pressure of 1 atmosphere. The gases combusted according to the reaction below. CH4 plus 2O2 gives you CO2 and H2O. Now calculate the pressure in the container after the reaction has gone to completion and temperature returned to 25 degrees Celsius. So what they're asking for in this question is the pressure. Now we already know the equation PV equals nRT, right? Sorry, PV equals nRT. Now here R is always constant. Temperature here was constant. Why? Because they said after the temperature has returned. So temperature never changed, so we remove it from our equation. The pressure is what we need to find, and the volume throughout the entire thing never changed. It was never mentioned, so it never changed. So V equals N now. It's not equal to N, but V is proportional to N. So we need to find the limiting reagent out of these. So we have here 1 mole, 2 moles, 1 mole, 2 moles. This has a molar mass of, you do RRGR. This is 1 mole and you have 0.5. And this is 2 moles and you have 1. I'm assuming, yeah. So what we're gonna do is 0.5 divided by 1, which is 0.5, and then so 0.5 divided by 1 gives us 0.5, and 1 divided by 2 also gives us 0.5. So here there's no limiting reagent. So this will also be 1 and 2 and 2 and 0.5. Wait, sorry, that's wrong. This will also be, 1, 0.5 and 2 and 1, because nothing changed. So what's written in the mark scheme is all the reactants will be consumed as moles of reactants are in correct ratio. So here the reactants turn into the products. Nothing is lost, nothing is gained. So then what we can understand is we used to have 1 atmosphere and we had not 1 atmosphere, it's P1 over P2 over N1, because it's P1 over P2, P1 P2 equals N1 N2, I think. I haven't done this equation in so long. It's P1 over N1 equals P2 over N2. So 1 atmosphere over 1.5 moles, which is what we had in the reactants, equals, I don't know how many atmospheres over 1.5 moles is what we had in the product. What they're trying to show you is that the moles in the reactants and the moles in the product stayed constant. 1.5 times 1 divided 1.5 gives you 1. So the pressure, if the number of moles in the reaction before and the number of moles in the reaction after did not change, the pressure will not change, because the temperature is constant and everything stayed constant. Nothing really changed. So our pressure is 1 and nothing changed at all. Like I said, I'm gonna skip all the examples because I don't want to solve the one wrong by mistake. And we're gonna move all the way to CQD 11. Now, a 0.150 gram sample of solid lead nitrate is added to 125 milliliters of 0.1 molar concentration of sodium chloride solution. No change in volume happened. The chemical reaction takes place, and this is the chemical reaction. This is the formula equation. So what's the observation that proves an evidence of reaction? Now what can we see? This S, which means a solid. What does that mean? A precipitate formed. Now we know that PbCl2 is lead chloride, and that's a white precipitate. We need to remember this from last year's material. By last year, I mean last term's material. So this is the formation of a white precipitate. That's our observation. So white, I don't know when I change the color. White PPT. Now calculate the number of moles in each reactant. So in PbNO3, they told us we have 0.150 grams. So 0.150 over the molar mass, which is, when you find it, 331, we are gonna get 4.53 times 10 power negative 4, I think. And for NaCl2, we had, we don't have for NaCl2 how much, but we could find it because this is milliliters. It's 0.125 liters, and this is 0.1 molar concentration, and N equals CV. So it's 0.0125 moles. That's how we find the moles immediately. So NaCl2 is 0.0125. And now I think that's it for part B. Identify the limiting reagent. So for the limiting reagent, we're gonna look at the number of moles. Here we have 1 mole, here we have 2 moles. So we're gonna divide the number, this is 125. I don't know what's up with me today and writing wrong numbers. Write the number divided by the thing. Here, I'm gonna do it here. So 4.53 times 10 power negative 4 over 1. And this is 0.0125 over 2. Which we're gonna get here 6.25 times 10 power negative 3. And this is the same number as this. I'm just gonna honestly move it because I can't rewrite it again. I barely have space, so you know what, who cares? Anyways, so now we need to compare the two numbers. 6.25 is obviously larger because negative 3 and negative 4. Since this one is larger, this is excess reagent and this is limiting reagent. So that solves part C. Now calculate the molar concentration of NO3 aqueous in the mixture after the reaction is completed. So what we have to do is follow very closely. So you have to multiply the moles of the excess times the limiting reagent, the limiting ratio we call it. This is called the limiting ratio. So multiply them, so you get 4.53 times 10 power negative 4. And then you divide it by the excess ratio. The excess ratio was 100, or no, wait, you divide it by the excess ratio, or wait. Okay, yeah. So we were finding the moles because they want the molar concentration, which is M, the concentration. So that's equal to M equals, or concentration equals to N over V, right? So to find the moles, we have the molar concentration of the limiting reagent, which is we have 2 here, right? We have 2 moles of NO3. So we multiply 2 by the limiting ratio and then divide it by the volume of how much lead nitrate we have, which is 125 milliliters, so 0.125. Then you divide everything, you get that it's equal to 7.25 times 10 power negative 3. And that's it. Honestly, these questions are like really annoying because they're asking for something and they ask for a million things and you don't know anymore what they ask for. Thus, yeah, it's not hard though, this chapter, if you focus. Now consider the reaction. N2 plus 3H2 gives you 2H3. Now, if 9 grams of H2 were reacted with 2 moles of N2, wait, what? This is the reaction. 9 grams of H2 were reacted with 2 moles of N2. Okay, yeah, my bad. 20.4 grams of NH3 were produced in the above reaction. What's the percentage yield of the equation? We know percentage yield equals theoretical yield, or it's actual yield over theoretical, my bad. Actual over theory times 100. So the actual yield was 20.4 grams. We need to find the theoretical yield. The theoretical yield is how much supposed to be produced. So it's 9 grams of H2 reacted. So we have 9 grams of this. And 2 moles of N2. Okay, yeah, my bad, because I was like reading my answer in the notebook and I completely confused myself. But like now I figured it out. So we have N2 and 3H2O, right? So we have 2 moles of N2. Here we have 1 mole, here we have 2 moles, and here we have, this is H2, I don't know where I got the O from. Here we have 6 grams, because H2 times 3. 6 grams. So 2 times that, so we're supposed to have 12 grams of H2. Except in the equation, they gave us 9 grams of H2 reacted. So we need to do a secondary equation. So, by the way, this means that N2 is in excess if we were supposed to have N2 was in excess if we were supposed to have 12 grams and we only had 9. That's what it means when you get an answer like this. So now we have to solve again, but this time with only the H2 and the N2. So we have 6 grams is what was given, or 6 grams is what's in the equation. 9 grams is what's given. So here we have 2 times 17 grams, which is 28. And now we need to find how much mass is supposed to be produced. So it's 51 when you cross multiply, of course. And now actual was what they gave us, which is 20.4. Theoretical is 51. When you multiply by 100, you get around 40%. And that's it for this question. Now we skip down and we go on to the top questions. Only 3. Again, we're back with the empirical formulas and finding formulas, as if we didn't do that enough. It's gonna be the exact same thing. We're gonna find the mole ratio of each one, then we're gonna, you caught the drill. But let's solve it anyways, in case there's something new, because if you look at the mark scheme, which I am looking at it right now because of the question before it, it has 14 steps to solving, but it does not need 14 steps. I think it doesn't. So combustion of 1557, the compound has 4 different elements. Oh my god. So the combustion of 0.1557 grams of this compound produces this much CO2, this much H2O, and then it's found that 0.13 grams of the compound produces 0.230. Yeah, there is a trick in this question, but shouldn't be hard. First, let's find how much carbon is produced. So the carbon produced is gonna be we do 0.213. We do the equation I showed you up times it's times, wait, isn't it times, wait, I forgot, what's it times? Oh no, that's to find the mass of carbon. We just need the O2 because there's O in this equation. So we just divide it by CO2, so it's 44, and we get 4.84, my gosh, I need sleep. 4.84 times 10 power negative 3. Then we do the same thing to find carbon, the moles of carbon. The moles of carbon are, sorry guys, so I went and the video cut and the writing went, so I'm gonna just restart this question because either way we were just like, let me just add a page in the middle somewhere because it needs like, I need a new page to solve it. Let me add this and I'll be okay. So let's read the question. It's about down here. So combustion, we have a compound that has C, H, N, and O, and we combusted 0.1557 grams of this compound. It produced 0.203 or 213 grams of CO2, 0.310 grams of H2O, and in another experiment, we found that 0.103 grams of the compound produces 0.0230 grams of NH3. Good. So now, what do we know? We know that we need C right now from CO2. Now, we know that the moles of CO2 are going to be the same as the moles of C. Why? Because there's only one carbon atom in C and there's one carbon atom in CO2. So the moles of CO2 are going to be 0.213 divide 44, which is going to give us 4.84 times 10 power negative 3 moles. Now we need to find the mass of carbon. To find the mass of carbon, we multiply this times 12, and mass of carbon equals 0.0581 grams. Now the percentage of carbon is, so what do we know about carbon in here? Or percentage, this is the total compound, and this is how many grams of carbon. So 0.0581 over the entire compound's carbon, or the entire compound's mass, times 100 gives us 37.0%. So this is the percentage of carbon. Now we're gonna do the exact same thing for hydrogen, except the moles of hydrogen equals 2 moles, or wait, it's 1 mole of hydrogen equals 2 moles of H2O. Why? Because there's 2 in H2O. So for hydrogen, you need to do 2 times the 0.310 grams over 18 to get it, because it's H2. Yeah? So now it's equal to 3.44 times 10 power negative 3 moles. Now, to find the mass of hydrogen, it's the same because you multiply by 1. Now to find the percentage of hydrogen, same thing we did up, divide by 0.157 times 100. We get that it's equal to 2.19% for hydrogen. Now, for this experiment, the moles of N are equal to the moles of NH3. So the moles of NH3 are 0.023 over 17, which is for N. Or is it for, it's for NH3, my bad. Equals 1.35 times 10 power negative 3. Now the moles for N is this number times 14, which is gonna give us 0.0189 grams. Now we need to find the percentage of nitrogen. Again, 0.0189 over the total, which is 0.103 times 100 will give us 18.4% for nitrogen. And now for last step, for oxygen, we're just gonna do 100 minus all of these to get how much is for oxygen, because oxygen is whatever is left. So 37, which is for carbon, minus 2.19, which is for hydrogen, minus 18.4, which is for nitrogen, will give us 42.4, which is for oxygen. Now we do the same thing we've been doing for the past few questions, percentage over molar mass to get your moles. This one gives you 3.08. Now 2.19 divided by 1 gives you 2.19 moles. Now 18.4 over 14 gives you 1.31, and 42.4 divide 16 gives us 2.65. Now we know that 1.31 is the smallest, so we're going to divide all of them by 1.31. This is going to give us 2.35. This is going to give us, when you divide by 1.31, it's going to give us 1.67. This is going to give us 1. And this is going to give us, divide 1.31, my bad. It's going to give us 2. Now you're going to, what did we say? When we have any type of decimal, what do? We have to multiply everything by either 2, 3, or 5 until you get every single one a whole number. So these, after trial and error, 3 is what worked out. When you multiply by 3, all of them are a whole number. So the first one's gonna be 7 for C. The H is gonna be 5. When you multiply this by 3, it's gonna be N3 and O6. So our compound is gonna be C7H5N3O6, and that's the answer to 12. So C7H5N3O6. This is probably the longest question in this entire chapter. Now for top question 13, it's telling you consider the reaction N2 plus 3H2 gives you 2NH3. If we mix 5 moles of N2 with 9 moles of H2, the diagram shows the mixture after the reaction. Assume it's a complete reaction. So what are they asking? If we mix, okay, I think they forgot to write what their question is. But the question is how many moles of ammonia should be left at the end of the reaction, I'm assuming. Is it? 1, 2, 3, 4, 5, 6. 1, 2. Yeah, I don't think this has anything to do with it, but I think I forgot to write the question. But based on the answer in front of me on the mark scheme, they want how many moles of ammonia are left. Or no, how many moles of nitrogen and how many moles of ammonia should be left. Oh wait, if they give us the picture, I think you can just count them. 1, 2, 3, 4, 5, 6, and 2 moles of nitrogen. But if you were to do it in what's it called, the correct way, without the diagram, because the diagram gives you the answer, you have 1 mole here, and they told you have 3 moles. Or wait, did they tell us we have 3 moles? No, you need to find how many moles. No, okay, you mixed 5 moles of N2. So Honestly, guys, for this part of the question, I genuinely do not know what they are asking. The mark scheme isn't making it that clear either. Like, it's telling you here that there's 1 mole, and here that there's 3 moles, here that there's 3 moles, and there's 9 moles. Ah, they did tell us we have 9 moles of H2. And, if we mix these with these. Okay, so you have, in the reaction, 9 moles of H2. Okay, and here you already have 2 moles. So how many moles do you have left of each? What you do, you cross multiply. 9 times 1 divide 3, so here you're going to have 3. Then 9 times 2 is 18, divide 3, you're going to have 6. So how many moles of N2 will you have left? You're going to have 3 moles of N2 left. Oh no, sorry, you added 5 moles. So if you add 5 moles minus the 3 moles, you're going to get 2 moles left. And here they didn't tell you anything about it, so you're going to have 6 moles left. So that's, I think, what they're trying to ask, but I think they forgot to write the question. Anyways, how many different isotopes we have? We have 2 isotopes because there's only 2 lines in this picture. So 2. Calculate the average atomic mass and identify the element. The average atomic mass, they're both 50%, right? No. Okay, so they're not 50% because I didn't see this. I was looking at the diagram. 51 times 79 plus 49 times 81. Can they just give us correct numbers? Like, what the heck? Over 100 should be 79.98. And you need to go back to your periodic table, which is going to be bromine. And that's the end of chapter 3. I hope you understood everything. This chapter is all stoichiometry and mostly no new formulas, everything we've done before. And yeah, next video is going to be about chapter 4 and the video after about chapter 5. These videos are all solving CQDs because these chapters are all solving. They have nothing really to explain.